Time for some discussion about covalent bonds and how they're interpreted in understanding molecular structure. As an architect can surely tell you, the structure is entirely important to how things function, including that really cool looking building. The learning objectives for this chapter that will be covered, first of all, are the discussion of the VSEPR model in predicting the geometries of molecules and polyatomic ions, even those that don't have only one, but more than one central atoms. That will be the topic for this first recording. VSEPR kind of looks like a funny acronym. It's valence shell electron pair repulsion model. Some folks like to make it pronounceable, but it doesn't really have enough letters. VSEPR refers to the notion that electrons in bonds and in lone pairs both can be thought of what we call charge clouds. In other words, regions of electron density that are very much negatively charged and therefore repel one another in a molecule, and they force the bond or lone pairs to stay as far apart from each other as they possibly can, and resulting in specific shapes. So specific shapes result from these bonds and lone pairs which are repelling one another in these charge clouds around a central atom. So you have to begin with an electron dot structure that's correctly done. You need to find all the bonds and all the lone pairs to know what the charge clouds are, and from that you can determine the molecular shape. So this is why our exercises in creating correct Lewis electron dot structures were important to begin with. The step one of working to explain molecular shapes using VSEPR is exactly that, to write the electron dot structure for the molecule, and then you count the number of electron charge clouds surrounding the atom of interest, remembering that an atom that is bonded to another atom is one charge cloud, as is a lone pair. And then using that, we will predict geometric arrangements of these charge clouds, assuming that these charge clouds are oriented in space as far away from each other as they are able to be. One can imagine each charge cloud like a balloon around a central point. Balloons cannot be squeezed together. Balloons tend to push each other apart, and that's what electronic charge clouds do as well. So what possibilities can there be? Well, the simplest one, of course, would be if you have two charge clouds around a central atom. Notice in this first example with carbon dioxide that there are two atoms connected to the central atom with double bonds, but each bond is one charge cloud, or double bond is a charge cloud region. In other words, the electrons between the carbon and the oxygen constitute one region of electron density. So with two charge clouds, the molecule is always going to be linear, and the bond angle is going to be 180 degrees. You can have a very simple symmetrical compound like carbon dioxide, or you could have a different one, hydrogen cyanide, HCN. Similarly, it has two charge clouds, but in this case they're two different charge clouds, a single bond and a triple bond, but each count as one charge cloud because they are the bonds connecting carbon to its neighboring atoms. So two charge clouds, you're always going to get 180 degree angles. Easy enough once you catch on to that idea. As long as you have an electron dot structure, it is easy to put these generalizations together. Notice that the lone pair of electrons on oxygens in carbon dioxide or on nitrogen in HCN have no bearing on carbon because they're not on carbon. So we're looking at the geometry around carbon for these examples. If you go from 2 to 3 charge clouds, then what results? Well, the first compound is called formaldehyde. Its formula is CH2O, and it has the carbon in the center, and it has single bonds to each hydrogen and then a double bond to oxygen. So that gives you 3 bonding regions around the carbon, and we call that geometry trigonal planar, and the bond angles are going to be roughly 120. Now, not always. In this case, it's more like 117 on one side and 122 on the other. In other words, there is a little bit of variation, but we call this trigonal planar geometry because they all lie in a flat plane with 3 atoms attached to this central atom. In this particular diagram, you can kind of get the idea that it's flat if you look at it correctly. The second molecule that shows three charge clouds here is SO2, sulfur dioxide. And this molecule, again, has three charge clouds, in spite of the fact that it might first not appear that way. Three charge clouds because you have two bonds, one to each oxygen, and one of them is a double bond, one's a single bond, and yes, resonance structures tell you that you could do them two different ways. And then there's also a lone pair on the sulfur. So each of those is a charge cloud for a total of three. And again, you get at bond angles of approximately 120 degrees, and we call this trigonal planar molecular shape, electron charge cloud shape. But the molecule instead is bent. Why? Because we only have two things attached to the central atom. You can't have trigonal planar without three atoms. So the molecule is not straight, not linear, because the lone pair of electrons influences the geometry of the electron charge clouds. The bond angle is still approximately 120 between the oxygen-sulfur angle. The lone pairs do make a difference in these geometries, so it's not just linear. So you can get three charge clouds and two different possible shapes. Both of them are based around a bond angle of about 120. One is called trigonal planar. The other is going to be only bent. Four charge clouds, next possibility. The angle you get from this is one that's less commonly encountered in your everyday existence. We call this a tetrahedron. The atom is in the center of this tetrahedral thing, where you have represented in this particular diagram a black sphere surrounded by four red ones, and they're singly bonded in this particular diagram. And if they're as far apart as possible from one another, that tetrahedron has a geometry with a bond angle of about 109.5 degrees, well, 109.45 or something, but we're not going to fight about that many digits. So the tetrahedral molecule will have this type of angle between any two bonds of 109.5. So with four charge clouds, what kinds of examples might we like to examine? The first one is the methane molecule, which is something you should remember by name from the last chapter. CH4 is methane, and it has four single bonds, two hydrogens from the carbon, so we call that four, and they're all bonding regions, no lone pairs on carbon, and so the bond angle checks out at exactly what we described. For a tetrahedral geometry, should be 109.5. If you have ammonia, ammonia might not be one we always remember, it's NH3. Ammonia is a molecule that has three bonds around nitrogen, but it also has one lone pair on the nitrogen. You can't see it when you're looking at the molecule, but it is conspicuously evident when we're talking about charge clouds. Three bonds and one lone pair add up to a total of four charge clouds. And again, the geometry is going to be based on tetrahedral bond angles, but the shape of the molecule has a new name. This is called trigonal pyramid geometry, because you have three atoms attached, and you think of the lone pair as being also on that central atom, but not viewed because they're not an atom to see, but definitely influencing the geometry of the hydrogens attached to the nitrogen here. So trigonal pyramidal molecular shape results when you have three bonds and one lone pair. The next example is good old water. H2O has two bonds, one each to hydrogen from the oxygen, and then two lone pairs on the oxygen. So those two lone pairs plus two bonds adds up to a total of four charge clouds still. The charge cloud geometry is still based on the 109.5 thought, but when you have lone pairs, it becomes a little bit distorted, and the bond angle becomes smaller, but we're not going to ask you in specifics about what that number becomes. Anyway, it's still close to 109.5. We can't call this molecule tetrahedral because it doesn't have but two things attached to the central atom. It's still not trigonal pyramidal either, but again, we have another example of something that looks as a bent molecule, in other words, not linear, because the lone pair electrons are going to push the hydrogens closer to each other than they might otherwise be if it was just linear, or even if it's only tetrahedral. So you get two bonds and two lone pairs, resulting in a bent geometry for water. Well, keep going. There's more possibilities yet. We call the next discussion around five charge clouds. So if you put the atom in the center and figure out what could happen when there's 5 charge clouds around a central atom, there ends up to be 2 kinds of positions around that central atom. 2 of them are described as axial, and the other 3 are described as equatorial. A little bit funky if you think about it, it kind of makes sense, but the red ones are in the axial positions where they're 180 degrees apart from one another, and then the blue ones are in a arrangement around the center atom in 120 degree angles apart from each other. So red to blue is a 90-degree angle, and blue to blue is a 120-degree angle. If you put all that together, we call that a trigonal bipyramid. In other words, if you put two triangular pyramids together, face to face on the triangular side, that's what you get here, and the blue atoms become the corners of the triangles. If you took 3 fingers off of each hand, a thumb and 2 fingers off of each hand, and press them together, it represents the same kind of thing as the trigonal bipyramid. If you look at this geometry top down, from starting at looking down from the red atom towards the center black atom, you can see on the right the 120-degree angle between the blue atoms. A little bit fun, interesting to look at. So what happens and what examples might there be with 5 charge clouds? Well, you could have all of the 5 being bonding regions. That's the simplest example. Phosphorus pentachloride molecule is an example of a compound that would have that type of geometry. Again, this would be something that's beyond an octet because apparently phosphorus has got 10 electrons around it in bonding arrangements. And so the geometry shown at the right there gives us two chlorine atoms in the axial positions, and then the remaining 3 are in equatorial positions. The angles will be 90 between the axial and the equatorial, and 120 between the equatorial positions, just like we showed in the previous example. So that's 120 on this side. Again, 3D drawings are a little bit funny to look at and not easy to draw, I agree. If you have something else, well, you could have 5 charge clouds total, but not all of them are bonding regions, just as we've seen with the other examples. And one possibility then is 4 bonds and 1 lone pair. Well, an example that has that is the sulfur tetrafluoride molecule that we perhaps discussed previously. Hope you might recall how to draw the electron dot structure. If you have counted up all the valence electrons, you realize that the sulfur atom needs to have, in addition to 4 fluorines, a lone pair on the central atom, resulting in 4 bonds and 1 lone pair, total of 5 charge clouds. And what happens when you do that? Well, you have to put the lone pair in a position that pushes, that is far away from other things as possible. And so it's going to be on that equatorial plane. And so you have 2 fluorines in axial positions and 2 fluorines in equatorial positions, and then the lone pair is pushing away from the 2 in equatorial positions to distort the angle a little bit, but we won't worry about that in detail. And the resulting shape is described as a seesaw. How's that for a fancy term? So it's a seesaw because if you turned it sideways like is shown on the right, you could envision the molecule being able to tip back and forth, resting on the 2 fluorine atoms shown at the bottom of the diagram. How about that? So 5 charge clouds, when there's 4 bonds and 1 lone pair, results in this funny thing called a seesaw. All right, more possibilities yet. 5 charge clouds can also occur with 3 bonds and 2 lone pairs. Chlorine trifluoride is a funny example, but it's certainly out there as possibilities. Chlorine trifluoride, if you add up all of the valence electrons, you determine that chlorine has to have 2 lone pairs on the central atom. Again, getting your Lewis structures correct is essential in understanding these. So if so, you've got 3 bonds to fluorine, and then the 2 lone pairs on the chlorine for a total of 5 charge clouds again. The basic angles are going to be based on that trigonal bipyramid, but where do the lone pairs go? Well, the lone pairs are going to be, in this case, as far apart as they can get from other atoms, puts them in the equatorial positions, and the remaining atoms become what we describe as T-shaped. Not very fancy terminology again, but that's exactly what it looks like, because the angles then between the fluorines with the axial and equatorial positions are all 90-degree angles, and I don't care how hard you look, that looks pretty much like a T. If you just turn it a little bit, it is a T shape. So 3 bonds and 2 lone pairs and 5 charged clouds in this particular example is what we call T-shape. Well, one other choice exists yet, and that is for a total of 5 to result from 2 bonds and 3 lone pairs. An example of that is the I3- ion. The name of that we won't go into more detail on at the moment. Not important to this discussion. When you figure out the valence electrons necessary for this compound, 3 iodines has 21 electrons, and a -1 charge means you have a total of 22 electrons. And the only way that's going to work is if you end up with 3 lone pairs on the iodine, which looks kind of funky, but so what? We'll just take that for what it is. And experimental evidence bears out that this structure makes sense. So 3 lone pairs end up all being on the central atom in the equatorial plane, and the 2 bonds are going to be in as far apart from each other. The atoms will be as far apart from each other as possible, and so that results in a very linear looking arrangement of the atoms because they're 180 degrees apart. Both are 90 degrees from the equatorial plane, but that adds up to 180. So there's a new way of getting a compound that looks 180-degree angles, and that is by having 3 lone pairs on the central atom in addition to the 2 bonds. Next possibility, 6 charged clouds. We won't go higher than that. The 6 charged clouds are going to be viewed as being at the center of a regular octahedron. You might not ever have heard of that term elsewhere, but an octahedron is something that's going to be full of 90-degree angles. There's going to be a top atom and a bottom atom that are in a straight line arrangement, and then there's going to be 4 atoms, possibly, around. There will be times where there will be lone pairs, of course, but around the central plane, and everything is 90 degrees apart from its neighbors. If you took the octahedral pattern that's shown in the center and view it from the top, it looks like a big X, if you will, and you can't see the 6th atom because it's straight behind the black sphere, and all the angles are 90 degrees. So how do these 6 charged clouds occur in specific examples? Sulfur hexafluoride, something we've been able to describe its name of in the previous chapter, has 6 fluorines on the sulfur in this octahedral geometry. It's 6 bonds and no lone pairs, and so it's not tricky. Everything has 90-degree angles. Whether you're looking at axial to equatorial, equatorial to equatorial, all the sulfur, fluorine angles are going to be 90 degrees. If instead we come to the next choice, and that is to have 5 bonds and 1 lone pair for your total of, remember we're looking at altogether 6 charged clouds for this section. 6 charged clouds that are all pushing each other as far apart as possible is no longer octahedral in geometry because one of those points is only a lone pair. And so if you look at the example with antimony and 5 chlorines, don't ask me the specific name here, that's not important. It has a -2 charge. It's an interesting ion that just fits this example. There's going to be 5 chlorines attached to the antimony, but there's also a lone pair. The lone pair ends up being on one side, and it doesn't matter how you turn it or how you draw it initially, but you can imagine it with the lone pair being at the bottom. All the angles being essentially equivalent, we end up with what's a square pyramid. In other words, those 4 chlorines around the bottom of this diagram become a square, and the remaining one is at the top, and just a lone pair at the bottom does not show in the actual molecular shape. The molecular shape now is called a square pyramid, but the angles are still going to be based on the octahedral electron clouds, 90-degree angles between the chlorine, antimony, and chlorine portions. So 6 bonds, 0 lone pairs, 5 bonds, 1 lone pair, guess what? You can do others. And so here's another one yet. What if you have 4 bonds and 2 lone pairs? That still adds up to 6 charged clouds. And xenon tetrafluoride. You know that's a weird compound if it's got xenon, but okay, it counts for an example here. And so if you do that, you can picture the two lone pairs as being as far apart from each other as possible. They would not be closer together. That wouldn't make sense. They're very much repelling each other. And the result is that you have no axial positions in this diagram, and everything is all in the equatorial plane. We call that a square planar geometry. Again, the angles between the fluorines in this compound, although that one at the right looks distorted from the side angle, it's going to be a 90-degree angle each time, both ways. So square planar is what you get when there's 4 bonds and 2 lone pairs around the central atom. Can there be others? Well, let's not go there at the moment. There is a nice summary chart in your textbook that gives you a way of recalling how to put all this together, but the more examples you see, the more sense it makes. Do make sure you focus on this chart to realize it's the number of bonds and the number of lone pairs that determine the total number of charged clouds. The total number of charged clouds gives us geometry and angles and the shape of the actual molecule. Various examples are shown here. All of the ones in this list are ones we've looked at. So recall then that whenever you have 2 bonds and no lone pairs, the angle is going to be 180 degrees. That's what we call it when it's linear. When we have a total of 3 charged clouds, whether it's all bonds and no lone pairs or 2 bonds and 2 lone pairs, the electron cloud geometry is going to be around 120 degrees. We can have either trigonal planar or bent geometries based on that bond angle. And when you have 4 charged clouds, either bonds or lone pairs or combinations of those that add up to 4, we're down now in the tetrahedral section where the bond angle is somewhere around 109, whatever, but not always exactly that. There will be distortions when there's lone pairs. And so the possible molecular shapes are going to be tetrahedral, trigonal planar, and bent. When you get to higher numbers, it's still the total numbers of charged clouds that give us geometry around each of the central atoms, whether it's bonds and no lone pairs or bonds with some lone pairs that add up to 5. We're looking at the trigonal bipyramidal, 2 pyramids with a triangle base stacked on each other, face to face, giving us the bond angles that are going to be 90 degrees between axial and equatorial, and 120 degrees between the equatorial and the axial positions. If you have lone pairs in these examples, they're no longer trigonal bipyramidal, but seesaw, T-shaped, or linear, with progressively more lone pairs in each of those examples, each of those options. When there's 6 charged clouds, you will have possibly bonds and no lone pairs, or bonds plus lone pairs adding up to 6. The geometry is based on the electron geometry being octahedral, but if there's some lone pairs present, we'll have either square pyramidal or square planar geometries for the entire molecule when there are 1 or 2 lone pairs on the central atom. Recall then that the angles in the octahedral geometry are all based around 90 degrees, but the overall shape, again, depends on how many lone pairs are present. The next set of slides, then, I will give you some examples of diagrams of molecules, and we'll try to describe the geometries that make sense in these compounds. Okay, so here's a compound for a molecule called ethylene. Ethylene has 2 carbons, and the remaining bonds are 2 hydrogens. And there's a double bond in the center, and a single hydrogen on 2 sides of the carbon in each case. So the center diagram shows you that the carbon has 120 degree angles around it with the bonding atoms, and each of the carbon has the same thing. The whole molecule is going to be planar with bond angles of 120 degrees. When you have 2 carbons with the same 120 degree angles and it's all trigonal planar, then the whole molecule is planar with 120 degree bonds, 120 degree bond angles. The example at the bottom of the screen is called ethane. You've heard of ethane. It's the two-carbon hydrocarbon that has two carbons, and apparently then obviously we can see 6 hydrogens. Each of these carbons has bonds to 4 atoms, and so with 4 bonds and no lone pairs on the carbon, the geometry becomes tetrahedral and the bond angles are 109.5. This is very typical geometry for all the hydrocarbons. Now, more examples. We're looking at the geometry around the central atom in each of these molecules, and we'll try to figure out the shape and the angles. Bear with me as I try to draw with my mouse. Okay, the geometry around the central atom in each of these molecules, we have to hope they've been drawn reasonably well. And what I see on the leftmost example, A, is we have 5 things attached to a central atom, and if they were equally distributed around the central atom, we would have trigonobipyramidal geometry, but it's not. Apparently, there must be a lone pair down here that's influencing the geometry around the central atom. And so instead, we have octahedral central atom molecular electron cloud geometry. The octahedral electron cloud geometry is going to have what kinds of, well, with one lone pair, we now call this square planar. There you go, square planar. Back up. No, it's not. It's not square planar.